Welcome, curious dreamer, to Science of Sleep. Tonight we embark on a serene voyage into an invisible fortress that shelters every heartbeat and every breath. Earth's magnetic shield. Picture yourself floating in the silent darkness above the North Pole, where no streetlights gleam and no engines hum only the ethereal glow of charged particles tracing unseen lines of force. Imagine the vast emptiness around you filled with delicate arcs of green, violet, and crimson as the solar wind's energetic gusts meet our planet's protective bubble. Where are you watching us from right now, and what time is it there? I'd love to know. Let me know in the comments below as our quiet journey unfolds. Settle into a comfortable posture and draw in a long, even breath, pulling in cool air as though you could inhale the faint auroral shimmer itself. Then exhale slowly, like solar particles slipping harmlessly past the barrier into space. That single, unhurried breath mirrors the steady balance of our magnetic field, dynamic yet unwavering. Beneath your feet, more than 3,000 kilometers down, lies the outer core, a roiling sea of molten iron and nickel heated beyond 5,000 degrees Celsius. In this molten crucible, hot, buoyant metal rises while cooler, dense metal sinks in a perpetual convective dance. Imagine a colossal cauldron in perpetual motion, its liquid currents swirling in columns shaped by Earth's rotation. Each swirl drags and stretches unseen lines of magnetism, wrapping them ever tighter and guiding them upward through layers of rock until they emerge above the surface. This self-sustaining dynamo, process first conceptualized by Michael Faraday and later refined by dynamo theorists, transforms mechanical motion into the magnetic force that surrounds us. With every rotation of our planet, the molten currents twist and amplify these magnetic lines, pumping energy into them like a vast generator. Those lines then burst through the mantle and crust, arcing into space to form the magnetosphere, a vast teardrop-shaped bubble compressed on the sunlit side where solar wind pressure is greatest, and trailing into an elongated tail behind Earth. On the night side, when a coronal mass ejection, a colossal eruption of plasma from the sun, surges earthward at millions of kilometers per hour. This shield deflects the brunt of charged particles. Instead of stripping away our atmosphere or frying electronics, most particles are guided toward the poles, where they collide with atmospheric gases and ignite curtains of auroral light in brilliant greens, purples, and reds. Now, let your shoulders soften and your jaw unclench. Feel your breath expand like a gentle tide beneath your ribcage, then release as smoothly as solar wind deflects around the magnetosphere's bow. That calm moment reflects the magnetosphere's guiding function, powerful enough to protect life, yet so quiet that most of us drift through our days unaware of its presence. Deep within this protective bubble lie the Van Allen radiation belts, two donut-shaped regions teeming with electrons and protons trapped by Earth's magnetic field, discovered in the 1960s by early explorer satellites. These belts spiral charged particles at near-light speed along magnetic field lines. Without them, satellites in low Earth orbit would be bombarded by radiation. GPS systems would fail, and astronauts would face dangerous doses of cosmic rays. Every navigational signal, every weather image, every high-frequency radio transmission owes its reliability to these invisible safety rings, which corral hazardous particles far above our heads. Let your awareness drift outward to the outer boundary of the magnetosphere, where solar wind and magnetic field reach equilibrium. Instruments aboard cluster and MMS missions have mapped this boundary in intricate detail, revealing how tiny fluctuations called flux transfer events carve narrow tunnels through which energetic particles can briefly slip inside. Although these breaches can spark magnificent auroras, the overall barrier remains intact, rebuffing most solar radiation. Observers in remote Arctic outposts watch for sudden ripples in the sky, flashes of color that dance to rhythms set millions of kilometers away on the solar surface, yet their radios crackle on without interruption, and their power lines carry steady current. On the ground, compasses still point toward magnetic north, though that north drifts over time. The magnetic poles wander unpredictably, guided by changes in the outer core's convective patterns. In the 19th century, explorers recorded the North Magnetic Pole on Boothia Peninsula in Canada. Today it lies in the Arctic Ocean, migrating toward Siberia at speeds up to 50 kilometers per year. Ancient lava flows preserve a record of these shifts, as basalt cools below its Curie temperature. Iron-bearing minerals align with the prevailing magnetic field, locking in a snapshot of field direction and strength. Geologists study these magnetic fossils to chart pole reversals epochs, when north and south swap places occurring on average every few 100,000 years. Each reversal spans millennia, and fossil records show minimal impact on life, a testament to Earth's enduring shield. Take a slow breath, letting your chest rise like the dome of the magnetosphere, compressed under solar wind. Then exhale as the field lines flow smoothly around our planet. That breath embodies the magnetosphere's unwavering protection, persistent, flexible, and vital. Beyond the poles, at lower latitudes, the field's strength is greatest near the equator. But its guiding influence spans the globe. High-latitude aircrews reroute transpolar flights during severe geomagnetic storms to avoid heightened radiation above the poles, where field lines converge and shielding is weaker. GPS satellites adjust their orbit determination algorithms to compensate for ionospheric disturbances caused by geomagnetic activity. Even power utilities monitor geomagnetic indices, wary that induced currents can overload transformers thousands of kilometers away from the polar regions. Meanwhile, life on Earth has evolved sensitivities to this magnetic tapestry. Salmon returning to their natal streams navigate by detecting subtle gradations in field intensity, using a magnetic map imprinted on their early migrations. Sea turtles, too, imprint the magnetic signature of their birthplaces. Coastal waters before heading out to sea, months or years later, guided by the same invisible cues. Migratory birds appear to visualize magnetic lines, perhaps via light-sensitive proteins in their eyes, overlaying a shifting grid upon their vision that guides them across continents and oceans. These remarkable behaviors rely on a stable, magnetic shield, one that has protected and guided life for eons. Above us, satellites such as swarm map Earth's field with unprecedented resolution, revealing small anomalies where deep rock formations and crustal variations locally tweak the field. In some regions, iron-rich ores intensify magnetic strength. In others, ancient meteorite impacts create subtle depressions in the map. Scientists combine these data with geological surveys to explore mineral resources and tectonic structures hidden beneath continents. On longer timescales, Earth's magnetic field plays a role in climate. By deflecting cosmic rays that ionize atmospheric molecules' nucleation sites for cloud formation, the field influences low-level cloud cover. Some studies suggest that weakened field conditions during pole shifts could modestly alter cloudiness and thus climate patterns. While these effects are small compared to greenhouse gas impacts today, the interplay between magnetism and climate underscores the field's pervasive reach. As your eyelids grow heavy, picture one final image: our blue planet wrapped in luminous filaments of force, rippling where solar storms tug, glowing softly where auroras bloom, its core's molten dance echoing in every compass needle and creature's instinct. This silent shield bends harmful particles, guides the migrations of fish and birds, and records a geological diary in every iron-rich rock and fossil. Let your breathing settle, each inhale and exhale, a gentle wave like the magnetopause pulsing. Under solar influence, our journey into Earth's hidden fortress continues in the next chapter, where we will explore the Van Allen belts and the delicate dances of charged particles trapped in those glowing rings. For now, hold the soothing protection in your mind as you drift deeper into calm curiosity, secure under Earth's invincible shield. Now that we have taken our first breath within Earth's invisible fortress, let us venture outward into the regions where charged particles dance in spirals, and where the magnetic field's true complexity unfurls. In this chapter, we explore the Van Allen radiation belts, the plasma sheet in Earth's magnetail, and the ethereal gateways through which solar particles slip past our defenses, igniting the heavens in silent fireworks. Imagine standing on the deck of a spacecraft, circling at 10,000 kilometers altitude, far above commercial air routes, yet still beneath the belt of medium Earth satellites. Around you, The sky is not empty, but alive with torrents of electrons and protons trapped by magnetic lines, forming concentric donuts of radiation. These are the Van Allen belts, named for physicist James Van Allen, whose Explorer 1 mission first discovered them in 1958. At altitudes between roughly 1,000 and 6,000 kilometers lies the inner belt, heavy with high-energy protons and electrons. Beyond that, starting around 15,000 kilometers, stretches the outer belt, where dynamic injections of particles from solar storms swell its population in minutes. These belts are not static donuts, but living rings that breathe in response to solar activity. During quiet space weather conditions, the outer belt settles into a relatively stable configuration, and satellites can pass through its edges with modest shielding. But when a coronal mass ejection or a fast solar wind stream collides with Earth's magnetosphere, a sudden compression of the dayside field can inject fresh particles into the belts. Within hours, the outer belt can swell, its electron density rising by factors of 10 or more. Satellites unprepared for this influx can suffer electrical discharge, single event upsets that corrupt onboard memory or disable critical systems. Operators in mission control echo ancient mariners' cautionary cries. Brace for storm, they warn, as engineers switch to safe modes and reduce power to vulnerable instruments. As your thoughts settle on these invisible hazards, take a moment for a slow breath drawing in air, as if breathing in the calm before a geomagnetic tempest, releasing it as smoothly as field lines deflect charged particles. That quiet interlude mirrors the magnetosphere's resilience, flexing under pressure yet maintaining a safe zone for life below. Beyond the belts, in the magnet tail that stretches far behind Earth on the night side, lies a region of turbulent plasma called the plasma sheet. Picture the magnetosphere as a windsock in the solar breeze, its tail trailing millions of kilometers behind us. Within that tail, two lobes of stretched field lines bracket the plasma sheet, a broad channel of hot, tenuous gas. Particles here drift east-west their trajectories, guided by electric fields induced as the solar wind's energy is transferred deep into the magnetosphere. Occasionally, the magnetail experiences a snap. Field lines reconnect suddenly, in a process analogous to stretched rubber bands releasing. This reconnection unleashes pent-up energy, accelerating particles earthward and outward. Those earthward jets plunge down field lines toward the polar regions, where they collide with atmospheric atoms at altitudes of 100 kilometers or more. Like raindrops hitting a pond, these collisions excite oxygen and nitrogen, producing shimmering auroral arcs that dance across the sky. In intense substorms, the aurora brightens and propagates equatorward, carving curtains of light that ripple and fold to the rhythm of reconnection pulses. Let your shoulders drop as you envision these substorms unfolding. Massive volumes of energy, comparable to hundreds of nuclear bombs released silently in space, lighting up high-latitude skies in luminous draperies. Feel your breath lengthen, matching the slow expansion of auroral ovals, then exhale as the arcs fade, leaving behind a stillness that echoes the magnetosphere's return to equilibrium. Deep within the plasma sheet, instrumentation from missions such as THEMIS, time history of events, and macroscale interactions during substorms and cluster has mapped layers of sheet current, known as the crosstail current. This immense current, flowing from dusk to dawn across the magnet tail, balances the pressure of the stretched field lines. Disruptions in this current trigger substorms and reconnection. Scientists have observed that during intense solar driving, the plasma sheet thins to less than 1,000 kilometers down from typical thicknesses of 10,000 kilometers, raising current density until reconnection is inevitable. These insights emerged from coordinated spacecraft measurements, each probe sampling a different region of the tail, then weaving their data into a three-dimensional tapestry of dynamic processes. As we drift further into the magnetosphere's outer reaches, we encounter the polar cusps, funnel-shaped gaps, near the dayside poles where magnetic field lines from the Sun and Earth mingle. In these cusps, solar wind particles have a more direct path to the upper atmosphere, funneled downward by converging field lines. Observers flying high-latitude transits sometimes report brief radio blackouts and high radiation doses when passing beneath the cusps, as energetic electrons penetrate their aircraft. Auroral emissions in cusp regions can take on unusual hues, rare purples and deep reds owing to the direct precipitation of protons and heavy ions. These localized features underscore the magnetosphere's complex choreography. Even as most particles are deflected, some slip through specialized doorways to interact with Earth directly. Take another deliberate breath, inhaling as though expanding your awareness of these hidden portals. Then exhale, letting the intricacies of plasma, field lines, and particles settle like sediment in still water. That moment of calm reflects how, despite countless interactions, the magnetosphere holds its balance, shielding us from the brunt of space weather. Turning now to plasma physics on smaller scales, consider the phenomenon of wave-particle interactions. Charged particles gyrate around field lines at frequencies determined by their charge-to-mass ratio and the local magnetic field strength, a motion called cyclotron resonance. Meanwhile, electromagnetic waves, Whistler mode waves, propagate along field lines, interacting with those particles. When a wave's frequency matches a particle's gyrofrequency, energy is exchanged. Electrons can be scattered into the Los cone and precipitate into the atmosphere, feeding diffuse auroras and depositing energy in the ionosphere. Alternatively, wave amplification can accelerate electrons to relativistic energies, bolstering the outer radiation belt population. Experiments on the ground using VLF, very low-frequency transmitters, have demonstrated this resonance, injecting waves into the magnetosphere to modulate belt electrons, an early step toward potential radiation belt remediation. As your mind digests these layers of complexity, reconnection, cusps, cyclotron resonance, breathe in once more, sensing the overlapping patterns of waves and particles. Exhale, allowing the interwoven processes to align into a coherent whole, a grand yet delicate system that both deflects and channels solar energy in ways essential to life. Returning closer to Earth, we find that geomagnetic storms can induce currents in Earth's crust and oceans, so-called geomagnetically induced currents, geysers. When the magnetosphere's currents reconfigure rapidly, time-varying magnetic fields penetrate the ground, creating electric fields that drive currents through conductive materials. Long-distance power grids can suffer transformer damage and widespread blackouts, as occurred during the March 1989 Quebec storm, when 9 million residents lost power within seconds. Pipelines and railroads feel the effects too. Geysers can accelerate corrosion and interfere with signaling systems. Geophysical surveys now map Earth's conductivity structure so that utilities can predict vulnerable regions and implement protective measures, reinforcing how the magnetosphere's remote processes echo down to our most grounded technologies. Breathe in quietly, imagining the electric fields swirling beneath your feet, as though you stood atop invisible waves of induction. Breathe out, letting the knowledge settle like cooled magma. That stillness echoes geologists' calm assessments when they integrate magnetotelluric data into subsurface maps that guide resource exploration and hazard mitigation. Shifting focus once more, consider the South Atlantic Anomaly, a region where Earth's inner Van Allen belt dips unusually low, bringing trapped radiation closer to the surface over parts of South America and the southern Atlantic. Satellites passing through this anomaly endure higher radiation doses and often power down sensitive instruments to avoid damage. The anomaly arises because Earth's magnetic dipole is offset from its rotational axis, and it's centered by several hundred kilometers, skewing the field strength and creating a weak spot. Geomagnetic observatories around the anomaly record lower field intensities and more frequent magnetic pulsations, known as micropulsations, testifying to the region's persistent vulnerability. Hold your breath briefly, feeling the subtle uncertainty that the anomaly represents, a reminder that even our planet's shield has its thin spots and shifting patches. Exhale, letting acceptance flow as calmly as iron licks its molten path in the core below. Our knowledge of these regions has grown through decades of satellite missions: ISEE, OGO, Themis, Cluster, Van Allen probes, and more. Each mission has carried instruments, magnetometers, particle detectors, plasma analyzers pointed outward into the void, gathering trillions of measurements that scientists stitched together to build dynamic models. These models now drive space weather forecasting centers, issuing alerts to satellite operators, power grid managers, and aviation authorities. As a result, our increasing understanding of the Van Allen belts and magnetospheric dynamics protects not only scientific satellites but the very fabric of modern society. Finally, note how these magnetospheric regions connect to the broader heliosphere, the bubble carved by the solar wind around the Sun's realm. At its outer boundary, the heliopause, the solar wind meets the interstellar medium, forming a cosmic shield that deflects galactic cosmic rays. Yet Earth's magnetosphere sits within this larger bubble, nested like a doll in a sequence, each layer conferring protection against ever more perilous radiation. The shielding hierarchy from heliopause to magnetosphere to atmosphere, life's fragility and resilience in the vast cosmic ocean. Let your breathing settle into its own gentle rhythm, each inhale and exhale echoing the spiraling particles, the pulsing waves, and the shifting fields above. Soon we will descend through our atmosphere, following those guided particles as they collide with air molecules, igniting auroral glows, reshaping atmospheric chemistry, and carrying whispers of distant stellar tempests. Until then, carry with you the magnetosphere's silent melody, a soothing dance of charged winds on invisible strings that ever guide and protect our world. And now, let us follow the paths of those charged particles as they spiral down from the magnetosphere into the upper reaches of our atmosphere, where they collide with air molecules to paint the sky in curtains of light and alter the chemistry of the air we breathe. Picture the ionosphere, a tenuous shell of ionized gas, beginning around 80 kilometers above the ground, pulsing gently as protons and electrons rain down along magnetic lines. When energetic electrons slam into oxygen atoms, they excite them, and as those atoms return to their ground state, they emit photons of emerald green or fiery red. Collisions with nitrogen produce deep purples, electric blues, and occasional flashes of pink. These auroral displays ripple and fold, a silent ballet conducted by solar storms and guided by Earth's hidden field. In this luminous theater, each arc and swirl corresponds to dynamics far above, currents of plasma shifting in the magnetale, injections of energy from reconnection, and oscillations in the field that modulate particle precipitation. Instruments aboard sounding rockets have sampled these phenomena directly, firing into the night sky to record particle energies, densities, and glowing emissions at altitudes unreachable by satellites. Those data reveal that auroral arcs can extend for thousands of kilometers, yet be only a few kilometers wide, razor-thin sheets of light slicing through darkness. As your shoulders soften with each sweep of color, feel your chest rise and fall, like the gentle expansion of an auroral oval around the poles, an unforced rhythm connecting you to space. Meanwhile, far below the visual spectacle, tiny changes transpire in the chemistry and conductivity of the upper atmosphere. Ionization enhances the ability of the air to carry electric currents, altering the propagation of radio waves. High-frequency broadcasts can skip off the ionosphere and travel far beyond the horizon, or, during intense substorms, be absorbed entirely, leaving remote outposts in sudden silence. Maritime pilots and aircraft crews listen for these ionospheric indicators, adjusting frequencies or flight paths to maintain communication. Even GPS signals, so crucial to navigation and machine timing, refract unpredictably when the ionosphere's electron density wavers, occasionally introducing errors of several meters unless corrected by dual-frequency receivers. Let your breathing mirror this interplay. Inhale smoothly, imagining electrons spiraling down magnetic funnels. Exhale steadily as photons flicker into existence. That breath reflects the coupling between space and atmosphere. Energy cascades from the sun to the magnetosphere, then to the ionosphere, and finally dissipates as light and heat in the upper sky. At lower altitudes, energetic particles deposit heat and ionization into the diregion of the ionosphere between 50 and 90 kilometers. Though invisible to the eye, this region affects very low-frequency VLF radio waves, ducting them around the globe in whisper-quiet channels that can be detected thousands of kilometers away. Researchers monitor these VLF signals to study sudden ionospheric disturbances, finding that solar flares can trigger nearly instantaneous changes in conductivity within seconds of the flares. X-ray burst reaching Earth. In that moment, amateur radio operators might notice a sudden surge or blackout on their receivers, an audible echo of solar fury refracted through our magnetic cage. As your eyelids grow heavy, recall that our atmosphere itself is shielded by this cascade of interactions. Ultraviolet and X-ray radiation from the sun ionize and heat the upper atmosphere. But without the magnetosphere's diversion of charged particles, the balance of atmospheric loss and replenishment could tip toward gradual erosion. On Mars, lacking a global magnetic field, solar wind has stripped away vast volumes of its atmosphere over eons, leaving behind a thin, cold shell, incapable of sustaining liquid water at the surface. Earth's robust shield preserves our atmospheric blanket, maintaining temperatures suitable for liquid water, stable climates, and the rich biosphere beneath. Deep in this ionized realm, coupling between neutral winds and charged particles generates dynamo currents that flow east-west across high latitudes. These currents close through the auroral electrojet's narrow bands of intense current that light up the sky in luminous green ribbons. Geomagnetically induced currents born from these electrojets can flow through long pipelines and power lines, sometimes triggering damage in regions far from the poles. Engineers now incorporate geomagnetic indices into grid management, installing blocking devices and rerouting power flows to prevent transformer damage during strong geomagnetic storms. Let your awareness settle on the silent rhythm of these currents as you draw a measured breath and then release it slowly. The invisible dance of ions and neutrals aloft mirrors the steady hum of life below, a subtle coupling that underpins modern technology and wildlife navigation alike. Not all interactions end in brilliance. Some particles descend deeper, colliding with oxygen to produce nitric oxide, which settles to lower layers and participates in ozone chemistry. In extreme storms, this production can temporarily deplete ozone locally, altering ultraviolet flux at the surface by a few percent. Small for a single event, but noteworthy in cumulative studies of climate trends. Atmospheric chemists track such variations to refine models of ozone recovery and greenhouse gas interactions. Meanwhile, radio scientists exploit ionospheric reflections to probe the Earth itself. Ionosondes send pulses of radio energy upward, measuring the height and density of ionized layers by timing the return echo. Seasonal changes in these layers, tied to solar cycles and magnetic activity, help researchers forecast communication conditions and study the dynamics of the neutral atmosphere below, since winds at 80 kilometers altitude feed back into ionospheric structure. As you drift through these layers with your mind's eye, remember that each glowing arc overhead and each silent shift in conductivity emerges from processes deep in the core, far above the ground, and from invisible solar storms. The ionosphere and atmosphere form a continuous chain of interactions that protects, guides, and sometimes reshapes our world. Allow your breath to lengthen once more, drawing in the calm of high latitudes, exhaling worries like scattered charged particles drifting off into space. That steady cadence echoes the magnetosphere's vigilant watch, bending solar fury and preserving the delicate envelope of our air. Soon, we will descend further, tracing charged particles as they penetrate to lower altitudes, influencing weather patterns and even climate over longer timescales. But for now, hold this vision of auroras, ionospheric currents, and silent chemical shifts, a testament to the unseen forces that dance above us, ever shaping the skies under which we rest. Our journey carried us from Earth's molten heart, through the magnetosphere's donut rings, and into the rippling curtains of the ionosphere. Now we descend still further, following trickles of energy as they seep into the neutral atmosphere and shape the climate systems we know on the surface. Imagine a single charged particle born in the sun's corona, hurled through space by a solar flare, then diverted by Earth's magnetic field toward high latitudes. It collides with an oxygen atom 80 kilometers up, producing a green photon in the aurora. But not all particles stop there. Some penetrate deeper into the mesosphere between 50 and 80 kilometers altitude. In this tenuous realm, the collisions create compounds like nitric oxide and hydroxyl radicals. Though minute in concentration, these species play outsized roles in atmospheric chemistry. Nitric oxide can catalyze ozone destruction temporarily, thinning the protective ozone layer above polar regions. Hydroxyl radicals drive oxidization of trace gases, influencing greenhouse gas lifetimes. Together, these processes subtly modulate the radiation balance and the chemical pathways that determine temperature and circulation patterns lower down. Allow your breath to drift slowly in and out, sensing the vertical layering of the atmosphere. Inhale, drawing you down through ionized layers into the denser mesosphere. Each exhale lifting you gently back. That rhythm mirrors how energy and particles cascade from space into the air we breathe, coupling solar influences to earthly weather. Below the mesosphere lies the stratosphere, home of the primary ozone layer. This region absorbs harmful ultraviolet radiation, protecting life on the surface and warming the upper atmosphere. Variations in ozone concentration can alter the thermal structure of the stratosphere, changing wind patterns that propagate down into the troposphere, where our weather forms. Sudden stratospheric warming's dramatic temperature rises in the polar stratosphere triggered by planetary wave interactions can shift the jet streams, sending cold Arctic air rushing southward into mid-latitude continents. Studies suggest that solar-driven changes in stratospheric ozone, modulated by geomagnetic activity, can influence the frequency of these warmings, thereby impacting winter weather in Europe and North America. As you exhale, imagine the winds shifting like invisible ribbons, carrying heat and momentum from pole to mid-latitudes. With each inhale, feel the calm before sudden stratospheric disruption, an analogy to the magnetosphere's own quiet before a geomagnetic storm. Descending further, we reach the troposphere, the lowest 30 kilometers of atmosphere, where clouds gather and weather unfolds. Here, cosmic rays play a curious role in cloud nucleation. When high-energy particles from space penetrate to these depths, they ionize air molecules, producing small clusters of charged particles that can act as condensation nuclei. Water vapor condenses more readily on ions than on neutral molecules, potentially increasing cloud droplet formation under certain conditions. More clouds can reflect sunlight back to space, cooling the surface, while fewer clouds allow more solar heating. Though the magnitude of cosmic ray cloud coupling remains under active research, some studies link periods of high geomagnetic activity, which deflect cosmic rays, to slight reductions in low cloud cover and modest surface warming. Conversely, during deep solar minima, when the heliospheric and magnetospheric shields weaken, cosmic ray flux rises, correlating with increased low clouds and surface cooling in regional patterns. Let your breathing trace these unseen processes. Inhale through imagined cloud banks forming on ionized seeds. Exhale as those clouds drift across sunlit skies. Each breath aligns you with the possible climate links between space weather and Earth's surface temperature. Turning our gaze outward, note that the magnetosphere and atmosphere also couple via electric fields. During geomagnetic storms, disturbances in the magnetosphere map along field lines into the polar ionosphere, driving strong electric fields and currents known as the polar electrojets. These currents close through the atmosphere down to lower latitudes, generating global-scale atmospheric electric circuit enhancements. Scientists have observed that such changes can modulate thunderstorm electrification and lightning frequency in mid-latitudes. Lightning itself injects nitric oxides into the upper troposphere, affecting ozone chemistry and radiative forcing. Thus, a solar storm's electrical pulse can, through a cascade of couplings, alter chemistry, clouds, and even lightning patterns thousands of kilometers from the poles. As you draw a calm, steady breath, visualize those electric currents flowing invisibly across continents, energizing thunderstorms and triggering flashes that illuminate the sky. Release the breath slowly, sensing how the most energetic space events can echo in the storms we experience on the ground. Meanwhile, satellites measuring microwave emissions detect changes in water vapor distribution following major geomagnetic events. Water vapor, potent greenhouse gas follows wind and temperature patterns influenced by upper atmospheric heating and circulation changes seeded by particle precipitation. Subtle shifts in humidity at certain layers can alter the propagation of infrared radiation to space, modifying the greenhouse effect in nuanced ways. Climate models now begin to incorporate these feedbacks, simulating how solar cycles and geomagnetic variations introduce small but persistent forcings over decades. In the deep tropics, the quasi-biennial oscillation, a cyclical reversal of stratospheric winds appears, modulated by solar activity. Researchers have noted that during solar maxima, the westerly phases of the oscillation tend to last longer, shifting rainfall patterns in the monsoon regions. These shifts influence agriculture and water resources for billions of people. While Earth's climate system is driven primarily by greenhouse gases and ocean heat content, these space-atmosphere couplings remind us of the broader cosmic context in which our weather and climate unfold. Take a long breath and feel the seasons. Shift within your lungs the moist monsoon air in summer, the crisp polar dryness in winter, ever guided by circulations that extend upward beyond the clouds into space. Exhale, letting the planetary rotations and oscillations settle into your consciousness. A slow syncopation of Earth, Sun, and wind. Finally, recognize that our protective magnetosphere also houses energetic neutral atoms particles that once bore charge but regained neutrality through charge exchange with atmospheric atoms. These atoms travel in straight lines, allowing imaging of magnetospheric boundaries from within. Instruments aboard missions like IMAGE and TWINS have captured all-sky maps of energetic neutral atom emissions, revealing the global response of the magnetosphere to solar storms. These images show storms compressing and expanding the protective bubble, offering a synoptic view of how space weather sculpts our environment. Now feel your breathing ease into a natural, unforced rhythm. Inhale and nod to the complex flows of charged and neutral particles above. Each exhale, a reminder of their quiet protection and subtle influence on our climate systems. As our exploration continues, we will drift back toward Earth's surface, tracing how these high-altitude processes imprint themselves on the waves, winds, and warmth that define our daily lives. Keep this tapestry of links in mind as we delve deeper into the coupling between space and sea, air and ice, unraveling more of the delicate threads that bind us to the cosmic environment. Under the subtleties of our planet's atmospheric shield lies another vast fluid reservoir that shapes climate and life, the oceans. Having traced energy from Earth's iron heart through the magnetosphere and down into the ionosphere and troposphere, we now turn our attention to the currents and chemistry of the seas, and how magnetically guided particles and solar energy together influence ocean circulation, marine ecosystems, and even the carbon cycle that regulates our climate. Imagine yourself on the deck of a research vessel cutting through glassy blue waters just beyond the polar circle, where seasonal storms churn the surface and deep waters rise to meet you. Above your head, charged particles guided by the geomagnetic field precipitate into high latitudes, producing auroral glows that drift lazily at the horizon. But beneath your feet, in the cold, dense waters of the polar ocean, a process begins that will carry surface properties into the abyss. The formation of deep water through brine rejection. As seawater begins to freeze into fragile ice and pancake ice, the forming crystals exclude salt, increasing the salinity and, therefore, the density of the remaining liquid. This dense brine sinks, cascading down continental slopes and trench walls and plumes that can travel hundreds of kilometers. These sinking currents form the start of the global ocean conveyor belt, transporting cold oxygen-rich surface water into the depths, where it fills the deep basins of the Atlantic, Southern, and Indian Oceans. Take a moment now to draw in a long, cool breath, feeling the crisp air of high latitudes filling your lungs. Exhale slowly as the heavy brine descends into the dark. In that single breath, you mirror the process by which surface waters, altered by ice formation, slip beneath lighter layers, carrying with them gases and nutrients that sustain deep-sea life. Once in the deep ocean, these high-latitude water masses travel equatorward along the ocean floor at speeds measured in centimeters per second. They mix over centuries with waters rising from the Indian and Pacific basins, gradually warming and losing density until they eventually upwelled back to the surface in regions of divergence, often in the southern ocean's storm-swept latitudes, or in eastern boundary upwelling zones off Peru and California. These upwelling regions teem with nutrients, fueling blooms of phytoplankton that form the base of marine food webs and draw down carbon dioxide from the atmosphere through photosynthesis. As you inhale, envision those nutrient-rich plumes rising, carrying microscopic plants toward sunlight. Exhale as you imagine the cascade of organic matter marine, snow sinking back downward, delivering carbon and energy to the deep on a timescale of weeks to months. That perpetual rain of detritus shapes the biological pump, a critical mechanism by which the ocean regulates atmospheric carbon and, by extension, global climate. Meanwhile, surface currents, driven by wind and modulated by the Coriolis force, guide warmer, saltier waters from the tropics toward the poles. The Gulf Stream, for example, carries equatorial heat across the Atlantic, moderating Europe's climate. These warm currents lose heat to the atmosphere, influencing weather patterns, and deliver salt to high latitudes, setting the stage for deep water formation once the water cools and becomes dense enough to sink. Allow your shoulders to settle as you breathe in the warmth of tropical seas, then breathe out, cooling toward the poles, mirroring the journey of heat that travels thousands of kilometers through ocean gyres. That single breath reflects the coupling of ocean and atmosphere. Winds drive currents. Currents transport heat, and this heat exchange governs both marine ecosystems and continental weather. Charged particles precipitating into the atmosphere can spark chemical reactions that alter rainfall patterns, which in turn affect river discharge and coastal salinity. Enhanced precipitation in monsoon regions can freshen adjacent ocean surface waters, reducing their density and inhibiting deep water formation. Conversely, reduced rainfall can increase salinity and promote sinking. These subtle feedbacks link solar storms to shifts in ocean circulation on regional scales. Take another measured breath, drawing in the idea of freshwater pulses from rivers and rains, releasing it as you imagine slowed sinking in the North Atlantic. That inhalation and exhalation echo how atmospheric electricity and chemistry, guided by the magnetic shield, reach down to modulate the ocean's deep circulation. In polar regions, auroral heating of the upper atmosphere can expand the thermosphere, increasing drag on orbit satellites, but also altering wind patterns at the mesosphere and stratosphere. Those altered winds can propagate downward, affecting storm tracks and size extent. Sea ice, in turn, insulates the ocean from the atmosphere and controls the rate of brine rejection. As magnetic storms heat the upper atmosphere in bursts, they may subtly shift size formation timing and patterns, again linking space weather to ocean dynamics. As you exhale, feel the interconnection. Magnetic storms above, atmospheric winds in the middle, ocean currents below, a three-layer tapestry weaving climate and life into a single, continuous flow. Ocean eddies, vortices, spun off from boundary. Currents also transport heat and nutrients. These swirling rings can trap water parcels for months, carrying them across basins and releasing their contents in distant regions. Eddy-driven transport influences plankton communities, fish migrations, and carbon storage. Satellites track sea surface height anomalies to map eddy locations, while autonomous floats profile temperature and salinity inside these spinning features, revealing their role in mixing and circulation. Breathe in slowly, picturing a warm core eddy spinning off the Gulf Stream, carrying heat and salt toward the north. Exhale, imagining its eventual dissipation and mixing into cooler waters. That rhythmic breath parallels the life cycle of ocean eddies, transient, yet vital to the ocean's health and heat distribution. Ultimately, the ocean's role as a giant flywheel moderates Earth's climate, absorbing excess heat and carbon, then releasing them over years to centuries. The coupling between magnetically guided atmospheric processes and oceanic responses underscores the complexity of our planet's system. As you settle deeper into calm awareness, remember that solar storms, magnetic fields, atmospheric chemistry, and ocean currents form a continuum, a planetary orchestra whose harmonies sustain the conditions we call home. Let your breathing ease into the natural tide of this vast system, each inhale drawing in connections from sea to sky, each exhale releasing the knowledge that life thrives under an intricate shield of magnetism, atmosphere, and ocean. Warm currents and sinking plumes have carried our attention from surface waters back to the silent depths of Earth's core. Now, as your mind drifts with the ocean's hidden rivers, let us follow the magnetic shield's imprint in rocks, life, and human endeavor. exploring how this invisible force has shaped continents, guided explorers, and now challenges our technology, and how those very challenges spur new innovations that may one day safeguard us better than ever. Deep within ancient lava flows, magnetite crystals record the direction and intensity of Earth's magnetic field at the moment. They cool below Curie temperature, roughly 500 degrees Celsius. Each eruption thus embeds a tiny compass needle in the rock. Geologists sampling mid-ocean ridges trace symmetrical stripes of normal and reversed magnetic polarity on either side of spreading centers, mapping seafloor, spreading like ribbons unfurling behind a sailing ship. These magnetic tapes not only confirm plate tectonics, but also chronicle hundreds of millions of years of geologic history. Supercontinents stitched and torn apart, ocean basins born and closed, and mountain chains raised by colliding plates. Pause for a slow breath-drawing in air, as though inhaling the deep past inscribed in basalt, exhaling as volcanic heat dissipates. That single breath mirrors the century-spanning cycles of polarity, flip, and lithospheric drift. Each exhale releasing fragments of forgotten worlds, carried on drifting plates. Beyond rocks, the magnetic shield has guided life's earliest wanderers. Long before compasses existed, organisms evolved. Magnetoreception cells with magnetite chains align like microscopic rods, enabling creatures from bacteria to birds to navigate by Earth's field. In deserts, migratory wildebeest may use the field's gradient to traverse vast plains. In the deep ocean, squid hatchlings chart courses using subtle magnetic maps. Recent studies show that some plants sense magnetic orientation to altering germination and growth patterns according to field inclination. In every root and wing and fin, the shield whispers a direction, weaving life's tapestry across land, sea, and sky. As you breathe in the notion of living compasses embedded in flesh, and breathe out the marvel that life interprets invisible forces, consider the evolutionary patience required for such adaptation, a process spanning eons. Far slower than human lifetimes, yet richer in context than any single lifetime can grasp. Humanity's adoption of magnetic knowledge began with simple lodestones and compasses, transforming seafaring forever. Medieval mariners relied on compass roses to cross vast oceans under uncertain skies. Portuguese explorers followed the needle, south along African coasts, reaching India under magnetic guidance, while Chinese treasure fleets steered to distant shores. Each voyage mapped the world more completely, trading goods and ideas, but all tethered to the invisible lines of the shield above. That tether grew ever more precise with the advent of magnetic surveys in the 19th century. Surveyors measured declination, the difference between magnetic and geographic north, charting isogonic lines across continents. Telegraph companies, laying thousands of kilometers of wire, learned to compensate for geomagnetic storms that induced currents along wires, disrupting communication. Nuclear physicists discovered that cosmic ray muons, influenced by the shield's strength, create measurable muon flux variations at different latitudes, leading to novel detection methods for subsurface structures and volcanic monitoring. Allow your shoulders to relax fully and draw in a breath as though absorbing the echoes of every compass reading ever taken. Exhale as you release the cumulative weight of those voyages, trusting again in the subtle force that guided so many explorers. From home, with technological progress, came new magnetic challenges. In the early 20th century, high-voltage power transmission lines spanning hundreds of kilometers experienced geomagnetically induced currents during storms, leading to transformers overheating and, in extreme cases, to widespread blackouts. Engineers began installing neutral blocking capacitors and real-time monitoring systems, turning once invisible currents into measured parameters. Pipelines traversing thousands of kilometers through permafrost and varied geology now require corrosion mitigation strategies tied to geomagnetic indices, preventing stray currents from rusting crucial infrastructure. Modern satellites are indispensable eyes and ears in orbit face relentless radiation pressure from trapped belt particles and solar storms. Engineers develop radiation-hardened electronics, magnetic shielding, and fault-tolerant software architectures so that onboard systems ride out relentless space weather. CubeSat missions test new materials that reduce charging and microthrust from Lorentz forces, ensuring these tiny voyagers can survive months-long missions. Even the International Space Station crew relies on magnetic shielding zones when conducting sensitive experiments in microgravity, using portable magnetometers to time operations during geomagnetic quiet periods. As you inhale, imagine the hum of power lines and the silent vigilance of Earth-observing satellites. Exhale with confidence in human ingenuity, our capacity to turn vulnerabilities into research opportunities, to measure what once was hidden, and to engineer around limitations imposed by cosmic forces. Looking forward, the steady drift of the magnetic poles poses fresh challenges. Airlines that once flew great circle routes over the true North Pole must now adjust flight plans as magnetic north migrates far from the axis. Navies chart submarine paths using magnetic anomalies of seafloor features, but those anomalies shift over decades as the core flow evolves, requiring continuous resurveys, rare earth mining for high-tech magnets. Crucial to electric vehicles and wind turbines, often targets igneous intrusions rich in magnetic minerals. As mines exhaust high-grade ores, geologists search new prospects guided by aeromagnetic surveys, detecting subtle variations in Earth's field that mark valuable deposits. Breathe deeply now, as if inhaling the promise of future energy transitions powered by precise magnetic technologies. Then exhale, mindful that the shield both nurtures and nudges human progress in equal measure. In the realm of science, paleomagnetism unlocks secrets of Earth's interior. Seismic waves traversing the core reveal it's not uniform. Some regions carry slightly different magnetic signatures, suggesting compositional variations and dynamic flows. Laboratory experiments at high pressures and temperatures replicate core conditions, testing how iron alloys conduct electricity and magnetism under extreme stress. Insights gained feed geodynamo models that simulate core convection, magnetic reversals, and secular variation. These models predict that the current weakening of Earth's field, the reduction of roughly 10% over the past 2 centuries, may presage a future reversal or excursion. Whether those changes pose risks to satellites, power grids, or navigation remains a subject of intense study, cautionary yet inspiring in its demonstration of planetary complexity. Allow your chest to rise with that sense of wonder and caution. Mix that knowledge of slow changes in our planet's core, shaping a shield that could transform yet again. Exhale, carrying forward an appreciation for the delicate balance sustaining life and technology under the cosmic breezes. Looking beyond Earth, comparative planetology illuminates the uniqueness of our protective envelope. Mars, with its patchy crustal magnetism but lacking a global dynamo, lost its atmosphere over eons, leaving behind a barren, windswept red world. Mercury hides a feeble global field within a partially molten core, carving out a miniature magnetosphere. Ganymede, Jupiter's moon, boasts its own dynamo, a magnetic oasis within a vast Jovian magnetic environment. Studying these worlds helps us understand the conditions necessary for habitability and guides the search for life beyond Earth. As spacecraft like Maven and Bepi-Colombo map Martian and Mercurian environments, they also refine our models of core, convection, and field generation, drawing connections between planetary size, composition, and magnetic longevity. Take a final gentle breath, imagining a loop through the solar system from Earth's molten core to icy moons with their own fields. Then exhale, letting this vast planetary context settle into your mind, a cosmic lullaby reminding you of our place in the universe. Soon, we will return to our own blue planet, tracing how the shield's slight secular changes imprint on climate records, on tree rings and ice cores, and on the cultural calendars of ancient civilizations that noticed shifts in celestial patterns. But for now, hold this exploration of core, life, and technology a testament to the magnetic shield's role as both guardian and guide in our endless quest to understand and thrive under its invisible embrace. We have traced our planet's protective barrier from its molten origins, through the magnetospheric realms and ionospheric dances, into atmospheric chemistry and into the circulations of the deep sea, then seen how that shield is recorded in rocks, sensed by life, and harnessed by human ingenuity. Now, as your consciousness drifts through these intertwined spheres, let us turn inward once more into the subtle pulses of the modern world, shaped by magnetism and its fluctuations, the rhythms of technology, the heartbeat of power grids, the flicker of digital networks, and the melodies of our own neural magnetism. Imagine standing in a data center humming with servers, thousands of hard drives spinning, and endless racks processing global information. Inside each drive, tiny magnetized domains encode the digital memories we cherish: photos of loved ones, archived literature, critical scientific findings. These domains rely on stable magnetic fields generated by precise current loops. Yet geomagnetic storms can induce minute voltages in long power cables, feeding such centers, risking data corruption. To protect against this, data centers near high latitudes install specialized surge protectors and redundant pathways regulated by real-time space weather monitoring. Engineers calibrate uninterruptible power supplies, not only for load balancing, but also to compensate for nano-upheaval, geomagnetically induced current fluctuations. In this way, the magnetic shield above indirectly safeguards the zeros and ones underpinning our digital civilization. As you breathe in, picture those data streams flowing undisturbed. Breathe out, trusting that silent shields guard your digital footprints. That breath echoes the invisible line of defense that bends solar fury away from delicate circuits. Beyond data centers, the electric grids that power cities face similar challenges. Long-distance transmission lines, spanning hundreds of kilometers, can act as antennas for geomagnetically induced currents. During intense storms, these geysers can saturate transformer cores, leading to overheating and potential failure. In March 1989, a powerful geomagnetic storm caused the Hydro-Quebec grid to collapse in just 90 seconds, plunging millions into darkness. Since then, utilities implement GIC monitoring systems that measure quasi-DC currents in transformer neutrals, model ground conductivity, to predict vulnerable regions and dynamically reconfigure networks during storms. These measures, forged in response to past failures, demonstrate humanity's growing mastery of correlations between space, weather, and power infrastructure. Let your shoulders soften as you draw in a steady breath, mindful of the unseen currents swirling along transmission lines. Exhale, releasing tension as the grid's safeguards hold firm against cosmic disturbances. In transportation, magnetism guides modern innovations from maglev trains that float on magnetic levitation to electric vehicles whose motors spin silently on magnetic fields. Maglev trains in Japan and China glide above rails with no physical contact, their superconducting electromagnets cooled to cryogenic temperatures, generating lift forces that counteract gravity and thrust forces that propel them at speeds exceeding 500 kilometers per hour. Engineers design control systems that adjust magnetic field strengths in milliseconds to maintain stable levitation, even as the Earth's background field sways with diurnal fluctuations. Similarly, electric vehicle motors employ rare earth permanent magnets and precisely timed alternating currents to convert electrical energy into motion. Battery management systems account for geomagnetic interference in current sensors, ensuring accurate power regulation and safe operation. As you inhale, imagine the silent hum of magnets lifting massive carriages. Exhale, feeling the efficiency of magnetic propulsion carrying you forward. That breath parallels the same principles that shield and empower our machines. Our bodies, too, are influenced by magnetism. Neurons in the human brain communicate via electrical impulses that generate faint magnetic fields, detectable by magnetoencephalogram MEG. MEG scanners record these picotessel-oval signals, mapping brain activity in real time. These measurements inform treatments for epilepsy, guide neurosurgeons in removing tumors without damaging eloquent cortex, and reveal how memories form. Modern MEG systems employ superconducting quantum interference devices, SQUIDs, that must be shielded from environmental magnetic noise, including geomagnetic fluctuations. Magnetically shielded rooms constructed of layers of mu metal and aluminum achieve noise reductions of over 120 decibels, isolating the brain's whispers from Earth's thunderous background. Researchers even time experiments to occur during geomagnetically quiet intervals, ensuring data fidelity. Let your chest expand as you breathe in the synergy between biology and physics. Exhale, recognizing how the magnetic shield not only protects, us from cosmic hazards, but enables us to probe the secrets of our own minds. In scientific instrumentation, magnetism underpins particle accelerators, where beams of electrons, protons, and heavy ions race along vacuum tubes, guided by powerful dipole and quadrupole magnets. Facilities, like CERN's Large Hadron Collider, use superconducting magnets cooled to -269 degrees Celsius to steer particles in perfect circular orbits, achieving collision energies that recreate conditions microseconds. After the Big Bang, these magnets demand extraordinary stability. A field variation of even 1 part in 10 million can defocus the beam, spoiling experiments. To maintain this precision, power supplies incorporate active feedback loops that compensate for diurnal ambient field shifts, including those from geomagnetic tides induced by lunar and solar gravity. Pause now and inhale deeply, envisioning electrons whipped into near-light speeds by unseen magnetic forces. Exhale, marveling at the precision that allows humanity to glimpse the universe's fundamental particles. That breath tribute, the same magnetic mastery that orients our compasses and shields our planet. Beyond science and technology, the magnetic shield has shaped human culture and mythology. Ancient civilizations revered magnetic stones, lodestones, as gifts from the gods. Chinese navigators used compasses for feng shui and geomancy, aligning temples and tombs with Earth's magnetic lines. In medieval Europe, sailors carried pocket compasses painted with fanciful windroses. Even today, artists incorporate geomagnetic motifs in sculptures that track field variations over time, transforming magnetic data into interactive light displays that pulse with real-time shifts. As you breathe in and out, let your mind wander to those lodestone seekers and temple builders, to the mariners trusting a floating needle under cloudy skies, and to modern creators turning data into art. Each inhale gathers the long thread of human curiosity. Each exhale releases it as inspiration for future journeys. Finally, let your breath settle into a tranquil rhythm. The magnetic shield hums around us, protecting, guiding, enabling. It links Earth's core to human consciousness, solar tempests, to neural storms, deep-sea currents to server arrays, and prehistoric compasses to particle colliders. That silent scaffold of force flows through every facet of our world. In this moment, rest in the calm certainty that the unseen barrier holding fast above continues its timeless vigil, allowing both wonder and sleep to flourish beneath its gentle embrace. We have journeyed from the molten churn of Earth's core to the silent depths of the oceans, traced charged particles dancing in the magnetosphere, drifted through the ionosphere's glowing curtains, and seen how space weather ripples into our atmosphere, climate, technology, and culture. Now, in our final exploration, let us rest beneath the invisible canopy of Earth's magnetic shield, reflecting on its deep history, its present vigil, and the possibilities for its future and ours in a changing world. Take a gentle, unhurried breath. Imagine inhaling the echo of every geomagnetic storm that has ever streaked across our skies, each exhale releasing the weight of centuries of cosmic encounters. That breath carries the legacy of countless solar tempests, deflected by the unseen force now cradling you in calm security. Millions of years ago, long before humans emerged, Earth's magnetic field underwent its first great reversals. Lava flows in ancient basalt provinces recorded these flips, each cooling flow preserving the orientation of magnetite grains aligned with the prevailing field. Those flows slipped quietly into the geologic record, chronicling epochs when the North and South poles swapped places. Life persisted through these slow transitions of atoms, but even a weakened, wavering shield continued to deflect the brunt of cosmic radiation. Fossil records show no mass extinctions tied directly to reversals, suggesting that our atmosphere, bolstered by the underlying magnetosphere, remains sufficiently protective. As you draw in air, consider the patient resilience of early life, forms thriving under a shifting magnetic embrace. Exhale, marveling that, despite planetary upheavals, the shield's essential function endured, enabling life's continual unfolding. Today, we stand amid a gradual but measurable decline in field intensity, about 5% weaker than 2 centuries ago. Observatories worldwide track the South Atlantic Anomaly, where trapped radiation dips unusually low above Earth's surface, and follow the meandering wanderings of magnetic poles, now moving toward Siberia at astonishing speeds. Shield models predict that these trends may lead to an excursion or full reversal within the next few thousand years, while a slower, less catastrophic journey than often portrayed in popular lore. Such a transition would challenge our reliance on technology finely tuned to current field conditions. Pause and breathe in slowly, sensing the subtle drift of the shield beneath your feet. Let your exhale release any anxiety about these changes, knowing that scientists and engineers are already designing robust systems to weather whatever fluctuations lie ahead. Looking forward, we can envision bold strategies to augment or mimic the magnetic shield. One proposal envisions a network of satellites carrying powerful electromagnets at the Earth-Sun Lagrange point L1, creating a deflecting dipole upstream of our planet to divert solar wind. While current technology limits field strength and power budgets, rapid advances in superconducting materials and space-based power generation might one day make such schemes feasible. As you inhale, imagine those orbital Sentinel-sleek spacecraft standing guard in the solar breeze. Exhale, embracing the notion that human ingenuity can partner with planetary forces to safeguard our home. Closer to home, localized magnetospheres could protect vulnerable installations. Lunar or Martian colonists may erect superconducting loops around habitats, generating fields strong enough to deflect local cosmic rays. On Earth, we might build geomagnetic shields around critical infrastructures, data centers, power grids, or hospitals using buried loop conductors that generate counteracting fields when sensors detect incoming gases. These systems could dynamically neutralize harmful currents, much like active noise cancellation, but for geomagnetic disturbances. Allow your breath to settle on that vision. A world where unseen defensive girdles silently activate in response to solar surges. Exhale, confident that the same principles shielding our planet can be scaled to protect human endeavor. Beyond physical shields, enhancing our predictive capabilities remains paramount. International space weather networks now share real-time solar imagery, magnetometer readings, and radiation belt data across agencies in dozens of countries. Machine learning algorithms sift through historical storms to refine forecasts of coronal mass ejections, flare intensities, and magnetic cloud orientations. These forecasts allow satellite operators to place spacecraft into safe modes, utilities to reconfigure grids, and airlines to reroute flights, minimizing risk and societal disruption. Take another deep breath, envisioning the global web of sensors and models working in harmony. Exhale, appreciating the collective vigilance that transforms raw data into protective action. Education, too, must evolve. Curricula in schools integrate space weather science alongside meteorology, teaching students about the interconnectedness of Earth and Sun. Citizen science initiatives invite communities to observe auroras, measure local magnetic fluctuations with smartphone magnetometers, and contribute to distributed datasets. Public outreach through planetariums, online simulations, and interactive apps fosters a sense of shared stewardship for the magnetic shield. As you breathe in, imagine classrooms alive, with students plotting field lines on globe models. Breathe out, envision a generation primed to honor and protect the unseen guardian above. In parallel, artistic endeavors translate magnetic data into soundscapes and light installations. Musicians compose pieces driven by real-time magnetometer readings, turning geomagnetic storms into symphonies. Visual artists create projections of auroral patterns dancing on urban canvases, connecting city dwellers to high-latitude phenomena. These cultural expressions deepen our intuitive sense of magnetic rhythms and foster a communal bond with planetary processes. Pause for a breath, letting the harmonies and colors of magnetic art fill your mind. Exhale, carrying that resonance into your dreams. On the scientific frontier, laboratory dynamos recreate core conditions, striving to understand how fluid flows in extreme environments sustain magnetic fields. Experiments with liquid sodium and advanced computer simulations illuminate the thresholds for dynamo action, guiding our expectations for exoplanets' magnetic properties. Knowing which distant worlds possess robust shields refines the search for for habitable planets in the galaxy. As you inhale, picture distant exoplanets spinning molten cores, each generating shields of its own. Exhale, reflecting on our privileged vantage beneath Earth's well-honed shield. In all these visions, space-based deflectors, localized habitat shields, predictive networks, educational arms, artistic echoes, and laboratory dynamos, the magnetic shield emerges not as a static artifact, but as a dynamic partnership between planet and people. Its health and function depend on our collective curiosity, vigilance, and creativity. Now, bring your awareness back to this moment. Draw in a final calm breath, feeling the invisible lines of force cradling you from below through the Earth's core, across the surface, and into the space above. Exhale, releasing any lingering tension, trusting that this silent guardian continues its ancient vigil. If this journey through the unseen realms of magnetism has kindled both wonder and tranquility, please like this video and subscribe to Science of Sleep. Share your reflections in the comments. Where are you drifting this evening, and what new insights has this magnetic voyage stirred in your mind? Thank you for joining this expedition into Earth's invisible shield. Now rest, carried by the steady pulse of magnetism, secure in the knowledge that an unseen force shelters every dream you dare to dream.